Welcome to Feza Gürsey Institute Higher Structures Seminars. Today, it's our pleasure to have Tatsuki Kuwagaki from Kyoto University, and he will going to talk on Introduction to Perverse Schober. So let's welcome him and let's thank him. Yeah, thank you. Yeah, please.
Thank you. Thank you for the invitation. Today I will talk about introduction to the subject so-called perverse schober. Actually, I'm not an expert on perverse schober, so maybe I can give only a very elementary part of introduction. And so, yeah, perverse schober is, in one sentence, it is a perverse sheaf of categories. So maybe it's better to start with an introduction to perverse sheaf. So, yeah, the first thing I should say is the Riemann-Hilbert correspondence. So it is some correspondence between two different kinds of data. So the first, one side is about a linear differential equation, usually over complex manifolds or complex domain. And if you solve linear differential equation, you will get a solution. It is complex analytic solution. And so since they are complex analytic solution and it is only defined a priori locally, so you will have some monodromy of solutions. So you will have such a map assigning monodromy of solutions to linear differential equation. And the very classical Riemann-Hilbert correspondence says that there is a correspondence between the set of linear differential equation up to gauge transformation and the monodromy of solutions. So the Riemann-Hilbert correspondence claims that you can recover linear differential equations from the monodromy of solutions. So for example, if you have this kind of linear differential equation over C, so it is defined, so Z is the coordinate of the complex plane, and you can solve this differential equation immediately by the solution Z alpha. But this Z alpha is not a global homomorphic function, but it has a monodromy around 0. So it is the singularity of the differential equation. And the monodromy is given by this, given by the multiplication by this number. But you have, for example, another differential equation whose solution is Z alpha plus 1, but the monodromy of this function is again the same exponential of 2 pi I alpha. And these equations are related by gauge transformation. So somehow on the left-hand side, we have kind of an equivalence class of linear differential equations whose equivalence identifies, for example, this with this. And such data is bijective with this kind of data. Yeah, so this is very classical Riemann-Hilbert correspondence. And you can reformulate this correspondence by using the notion sheaves. So sheaf is somehow, so I will only first talk about sheaf of vector spaces, but sheaf assigns vector space to an open subset of the base manifold, base topological space. So in this Riemann-Hilbert context, our sheaf is for an open subset U, we get the vector space of solutions of this differential equations, this differential equation on U. So somehow, for example, on U, we have the one-dimensional vector space found by the alpha. Also, maybe here you have this kind of vector space, and here you have this kind of vector space, and so on and so on. And by connecting this chain of open subset, you will get some discrepancy, which is a monodromy. Discrepancy of the identification, which is a monodromy. So somehow, yeah, the assignment of a vector space to this kind of open subset is seems like constant, since they are all the same vector spaces. But going around the singularity, you will eventually get some exotic identification. So this situation, we say it forms a locally constant sheaf or local system. So as we have seen in this picture, this data of locally constant sheaf or local system encodes the data of monodromy. So little modern formulation of the Riemann-Hilbert correspondence says that we have a bijection between the set of differential equations, linear differential equations, or some so-called regular linear differential equations up to gauge transformation, and the set of local system. So somehow an advantage of the use of local system rather than this more primitive language of monodromy is this local system does not have any base point choice, so does not include the choice of base point. So it's more, how to say, coordinate free data. Okay. So at this point, we have on the right-hand side, the topological side, we have.
Can you say that again? I didn't understand. What's the choice of coordinate in monodromy? There is no.
Okay. So if you want to consider, okay. So when I say the monodromy is this E exponential of 2 pi I alpha, then it's implicitly I'm taking a choice of a base point and consider a solution at this point, and then I take the analytic continuation of this solution, and then I will get after going around the singularity, I will get this kind of modified solution, and so this discrepancy is the monodromy. But so somehow this data expresses a representation of fundamental group. So to talk about the fundamental group, you have to take you have to choose a base point. But in the language of local system, you don't.
Okay, so you're more talking about the base point in this example. You're talking about the base point because there is no choice of coordinates that you need to talk about the monodromy. Just base point, yes. So this I agree. Yes.
Sorry, maybe I said something different. Sorry. Yeah.
You could use the representation of monodromy groupoid or something like that, maybe, to get rid of that.
Local system is just a fundamental representation of fundamental groupoid. Yes. Yeah. Is it okay? Thanks. So in this setup, you have a correspondence between differential equations and the local system. And of course, differential equation is also, local system is somehow, local system or sheaf is somehow local data. And of course, differential equation is somehow something locally defined data. So you can formulate differential equation in terms of shapes. So for this purpose, we introduce so-called D modules, the language of D modules. So this D stands for the ring of differential operators. So it is, in very elementary case over the complex plane, you have this kind of ring. So it is generated by two indeterminates and subject to the relation, usual relation. And so D module is just a module over D, but you can consider it as a kind of generalized differential equation. So for example, from this differential equation, you can cook up a module over D, which is this D module, which is D quotient by the ideal generated by this element inside D. And in this language of D module, you can also formulate a solution of differential equation. So a solution of this differential equation can be interpreted as a D module homomorphism from this D module to very standard D module, which is the structure sheaf or just this one. And you can consider usual differential action. Then from psi, if you have some operator here, you can define p psi, and then since this operator this operator kills this function, you will get a well-defined homomorphism. So in this way, you can somehow talk about analysis of differential equation in terms of D modules. And the point is this, this ring of differential operator forms a sheaf, and sheaf over the base manifold, and also D module forms a sheaf over the base manifold, and this is somehow sheafy expression of differential equation. Of course, of course, if you know the language of connection is also that's kind of sheafy or local language of differential equation, but somehow the virtue of the language of D module is that it includes also the singularities. Maybe I will touch it soon. And so now this statement can be rephrased as that the Riemann-Hilbert correspondence says the correspondence between certain D modules and certain D modules and local systems. But if you look at the definition of D modules, you will have more and more, generalized differential equations. So for example, you can consider this kind of D module. And obviously, since this D module corresponds to this differential equation, this D module should correspond to this kind of equation. But it is very exotic differential equation. There are no differentials, but you can still try to consider solutions of this differential equation. And so one possibility to solve this equation is by delta function, Dirac's delta function. Since delta function only supports at zero, if C is non-zero, you can solve it as psi equals 0, and if Z equals 0, then arbitrary psi works. But since psi is 0 outside z equals 0, it should be kind of delta function. So if you want to extend this kind of Riemann-Hilbert correspondence to this kind of D module, you have to think about monodromy or solution sheaf, monodromy or corresponding local system to this delta function. So an obvious candidate is skyscraper sheaf. So it is just a sheaf which, if open subset U contains 0, it assigns C and otherwise 0. So yeah, it expresses situation that we only have non-trivial solution at 0. So, and there is a notion of constructive sheaves, which is a generalization of both local system and skyscraper sheaves. So note that a local system is somehow kind of locally constant assignment. Constant assignment of vector spaces. The skyscraper sheaf is, it only supports at 0, but supports at 0, but if you restrict it to 0 and C minus 0 respectively, you will get locally constant sheaf on 0 and C minus 0. So in that sense, skyscraper sheaf is piecewisely local system, piecewisely locally constant sheaf. So in each piece, or over each piece, you have a locally constant sheaf. And so there is common generalization of local system and skyscraper sheaf. It is constructive sheaves. So it is somehow, you have a kind of piecewise decomposition into pieces of the base manifold, and over each piece you will have a local system, which is so that kind of object is called constructive sheaf. Okay, now I can state the regular Riemann-Hilbert correspondence proved by Doreen and Kashwara and Bebek. And so it is, so at this level, so maybe first you should ignore this one. So what I have said is, if you have a D module, so again, certain kind of, we have to assume certain assumptions on the D module. So maybe. So this is assumption for that to get the solution, to make the solution space reasonable size or for finite dimensional, finite dimensional over C. And this is certain assumption on the singularity, tameness of singularity. So assuming such certain assumptions, the modules can be mapped to constructive sheaves. So for example, this kind of D modules are satisfies assumptions, the regular holonomic, and under the functor, you will get this local system and the skyscraper sheaf. But skyscraper sheaf. But yeah, up to shift. So yeah, so the thing is not so straightforward. So you don't have equivalence between this regular holonomic D modules, the category of regular holonomic D modules and constructive sheaves, but you have to take the derived category of two categories. So you only have an equivalence between derived category of regular holonomic D modules and derived category of constructive sheaves. So inside this category, you have a complex of D modules, and also on this side, you have a complex of sheaves. And moreover, this equivalence does not induce equivalence between D modules and constructive sheaves. So if you have a Junane D module, it corresponds to not a constructive sheaf, but a complex of sheaves. But still, you can characterize the essential image of this kind of pure D modules under this Riemann-Hilbert equivalence. So it is the notion of power sheaves. So under the Riemann, I have already written it. So under the Riemann-Hilbert equivalence, you will not get an equivalence between these categories, but you will get an equivalence between D modules. I mean, not complexes, D modules and power sheaves. And power sheaf is in general a complex of sheaves. Let me give a formal definition of power sheaf. So it is a priori just a complex of constructive sheaves, but is a power sheaf if these two conditions are satisfied. So the first condition says that, so you have, yeah, this F is complex. So yeah, so you have this kind of complex, and HIF is just a usual cohomology sheaves, so kernel D I. And the condition says that the support of such cohomology sheaves at degree I has dimension less than or equal to -I. And the second condition says that, so on the category of, on the bounded derived category of constructive sheaves, there is certain duality factor, duality of constructive sheaves. It is so-called Verdi duality. And you will assume the same condition for the dual constructive sheaf.
Sorry, what do you mean by -I? Do you mean like codimension is I or something like that? What does -I dimension mean?
Oh, I is just integers, so it is only meaningful if I is non-negative.
Oh.
Yeah. So yeah, so this condition says if I is positive,
these are unbounded complexes. These are unbounded complexes. So they're not.
sorry, this is maybe other result. This is bounded, but yeah, maybe you can assume, but I think it's equivalent. Yeah.
They're bounded, but they can be okay.
They can be negative. They don't have to be unbound.
Yes. Okay. Thank you.
Mm-hmm. Okay, so maybe this definition is not so intuitive. So maybe let me give some examples. So let us consider the case when the base manifold is unit to disk. This is base manifold. And as I said, so perverse sheaf is a complex of constructive sheaves, and constructive sheaves are kind of piecewise locally constant sheaves. So let me assume that. So for the simplicity, let me assume that the pieces of constructive sheaves are D and 0. So I mean, so it means the restriction to 0 and D minus 0 are complexes of local system. Let me assume such a condition for perverse sheaf. Then I can describe some examples. For example, this constant sheaf shifted by 1 is a perverse sheaf. So yes. So for example, if you consider the degree of 1 minus cohomology, then you will get KD. So this the support of the dimension of the support of this KV is 1. And since here is -1, we have here this -I is -1. So it satisfies the condition. And I didn't introduce the Verdier duality, but if you compute it, the Verdier dual of this sheaf is this is a self-dual object. So this is a self-dual object. So the condition for the dual sheaf is obvious from the first one. And also a skyscraper sheaf is
I don't know if you mentioned, maybe I missed it, but I guess it's also one characterization of perverse sheaves is that the Verdier duality preserves them, right? So Verdier dual of a perverse sheaf is perverse.
But Verdier dual of perverse is perverse.
Yeah, this is implied by this condition, I guess, but yes.
Say that again? Sorry.
It's implied from the support condition as well, I think. But
yeah. It is implied by this condition. Yes. But yeah. Maybe you know, but the Verdier duality preserves the perverse sheaf does not mean the self-duality. I mean,
yes, of course. Yes.
Okay. So skyscraper sheaf satisfies the condition if the non-trivial homology sheaf is only at 0 and the support of K0 is 0, so the condition satisfied. And also this K0 is self-dual, and you can check. You can check the second condition, obviously. So they are perverse sheaves. And also there are some perverse sheaves. For example, this kind of the 0 extension or Schlick extension of the constant sheaf over d minus 0. Also, yeah, if you have a non-trivial monotomy around 0, the Schlick push is +1 shift is a power sheaf, and also the usual push forward is also a power sheaf. In this context, and the Bellier dual relates these two sheaves. Yeah, I will not check this since it's a little, yeah, not hard, but a little hard.
Sorry, maybe I'm asking something impossible, but is that, I mean, I heard this Verdier dual functor millions of times, but I never understand. And do we have any, since we started everything kind of very basic and so on, maybe there's a way to motivate it or give some kind of intuition about where the dual operator is coming from?
Yeah, Bellier duality is just a kind of categorical lift of the Poincare duality. Yeah.
Yeah, but well, I mean, now we started the whole discussion with the differential equations and so on. Like, you know, why did we start talking about some categorical version of Poincare duality?
In the setting of differential equation, you mean?
Like,
oh.
I mean, is there a way to motivate this in a way that kind of fits to how you're presenting the?
Let me see.
It might be impossible. I've never seen anyone actually give me something super.
Yeah, but under the Riemann-Hilbert correspondence, the category of differential equation is equivalent to the category of local system of constructive sheaves.
Yeah, I understand that there is such a result, but where is it coming from? Like, well, how could I have guessed that there is going to be some appearance of the Verdier dual before you proved the full result? Is there a way to expect it? Or?
Yeah, if you like a categorical nonsense, you can expect the Verdier duality from the existence of Schlick-Purback or something like that. Since Schlick-Purback is somehow very abstract consequence of the categorical nonsense, so it's very natural. Sorry, I'm not. I don't have any good explanation. Sorry.
Like maybe I can ask this: what does Verdier dual correspond to on the holonomic D module side? Maybe that's something that you can say.
Yeah, it's just yeah, it is. Yeah, it is something like the same kind. So yeah.
Maybe in an example, even we can do it. Maybe in this very simple example with solutions being z to the alpha. What do I?
Okay. So yeah, but if you have it, so this if this alpha is yes, let me see. Yeah, if this alpha is not integer, the Verdier dual is just, I think, just the local system with inverse monotomy. And if you have a trivial monotomy around it,
so then this kind of sends alpha to minus alpha. Is that
alpha to alpha? I think alpha to alpha inverse. Sorry. Yeah, minus alpha. You are right. You are right. The monotomy is inverse, right? Yes. Yeah.
Okay. Well, that's an example that I can keep in mind. Thank you.
That's great. Okay, now let me go to the topic power schober. So the notion is due to Kaplan-Schichtman, and in some sense it's still conjecture. So, but yeah, somehow there are some ongoing program due to Kaplan and the courses, but we already have some tentative definitions and many examples. So yeah, let me repeat. So in this talk up to now, so power sheaf is power sheaf of vector spaces. So it is certain complexes, certain complex of constructive sheaves. And a power schober is a power sheaf of categories. So in other words, it is a categorification of power sheaves. So, but this is somehow philosophical or slogan. So power schober should be a mathematical object consisting of categories and functions and some relations, and which gives you a power sheaf after taking some decategorification. So decategorification means, for example, by taking the glutonic group and tensor C, or taking whole sheet homology and some factorial after taking some factorial decategorification, you will get a power sheaf. Power schober is a kind of such object. And there are several motivations to consider such objects. For example, there is a notion. I don't explain very much, but there's a notion of quasi-ideal category. So it is very important in the context of mirror symmetry or symplectic topology, and it is a categorification of vanishing cycle and intersection of them between them. And yeah, usually if you have a, for example, polynomial singularity or something like that, you should consider the vector space of vanishing cycles and intersection of between them, and then the lattice structure of such vector space will classify the singularity or something like that. And quasi-ideal category is the categorification of that. And but such vector space of vanishing cycles is fit into a power sheaf picture, since if you have this kind of geometry, and if you have a vanishing cycle here and it vanishes at the singularity, then you will have a local system spanned by whose stalk spanned by these cycles, and at the singularity you will have a little different behavior, but it forms a power sheaf. So I mean more elegantly, if you have a structure sheaf on this total space, you should take the powers push forward along W or something like that. Anyway, so this vanishing cycle picture can be fit into more kind of global geometric picture. So since the vector space of vanishing cycles can be fit into a power sheaf, it is natural to expect that quasi-ideal category will be fit into a power schober. So it is a categorified power sheaf of this power sheaf.
Sorry, I have, maybe it's again an annoying question, but I mean, I've been seeing this slide for maybe the last 10 years. And it's always at the same level. It's always that you expect. So is there a reason why this expectation has never really turned into something?
So one reason is maybe so one reason is anyone didn't this research, I think. but one possible reason is somehow constructing a power schober from from this Lefschetz geometry is not so difficult, but the problem is we yet do not have a good definition of our schober. So people don't want to do it. Just yeah, is it? I'm not sure. For example, Matt, you are a symplectic topologist, right? So you don't find any difficulty to construct it, maybe.
No, this is wrong. It's. I mean, there are many technical. I mean, no one actually worked out. Like there is a local definition where if you have a single singularity, for example, you can define kind of something like a hypersurface singularity, and you're kind of only interested in the Milnor fiber and kind of the small scale geometry around the singularity, then there is kind of well-defined notion. But if you have like some kind of tame polynomial from C to the N to C, something that's supposed to be very standard, I think there are some difficulties.
But
like the difficulties are more technical though. It's about kind of holomorphic curves escaping to infinity and things like that. This kind of more technical, but it's not a fully kind of resolved thing. It's I don't think it is. Yeah, so, I think people just keep talking about this stuff as if somehow like everyone knows everything and we just need a definition. But I just wanted to hear your opinion about. But you're saying it's because kind of you don't believe that the algebraic definition is correct yet, so it's not kind of worth putting so much effort into.
Yeah. Also, maybe I don't know, but constructing this this Fukaya-Zeidel schober itself is not so interesting, I think. Yeah, since
I don't know. I mean, people have been giving this talk and saying it's very interesting, and I don't know who to believe. Is it interesting or is it not interesting? I haven't seen any actual definition or anything like that.
I think this is just a motivation, and it's kind of constructing this is not so, let's say, benefit. Or I'm not sure.
This should be just thought of. Okay.
Yeah, but yeah. This is very kind of motivating example. So you can readily imagine the existence of the notion of perverse schober. That's good. Okay, also there's motivation from mirror symmetry. And so homological mirror symmetry says that there is equivalence between derived category of coherent sheaves and Fukaya category. And also mirror symmetry says that you will have an isomorphism between so-called Kähler modular space and complex modular space between mirror manifolds. And yeah, people expect that so the derived category coherent sheaves form a local system of this Kähler modular space, and the Fukaya category forms a local system of a complex modular space. And yeah, it is expected that the homological mirror symmetry should be lifted to an equivalence between such local systems of categories. And also, this local system.
Can I ask a question? So is it obvious that this local system is not just trivial on the right-hand side? I mean, Fukaya category is supposed to not depend on the complex structure.
But yeah, it does not depend on, and the monodromy is different thing, I think.
Huh? No, this is very interesting. I had never seen this. Is this worked out anywhere?
I don't know, but at least you, for example, maybe I should take the quotation mark here, but for example, yeah, I'm not sure it's a correct example or not, but for example, I and Will Donovan did some, but it's not Caravia, but in Fano or some more random Ginzburg type geometry, we have some autoequivalence coming from the modeling around the singular point of the how to say?
No,
but on the B side, you have a bunch of example, right? And on the B side, you have a bunch of example, and in classical mirror symmetry, you should expect the more equivalence isomorphism between these spaces. So there should be an example.
I mean, I don't know. To me, I could ask the same question on the left as well. If you just fix the complex structure and change the Kähler structure, then why should the category of coherent sheaves have any interesting dependence? It just seems like a trivial sheaf to me. Seems like a trivial local system to me, but you're saying that it's not. I don't.
Yeah, somehow. That's a good question. Yeah, somehow you're right. So of course, DB co-X does not depend on the Kähler structure, but so from many evidences, like the Robbins conjecture or something like that, the constant sheaf on the string as the constant sheaf valued in DB co-X value supported on the string Kähler modular space is not a correct object. You have to construct a local system whose monodrome is a categorification of this quantum differential equation. It is a very strong. There are very strong evidences. Yeah.
I mean, yeah. Sometimes there's some kind of Kähler moduli where the cohomology class actually doesn't change. There are some kind of open symplectic manifolds. And then you can kind of again have this kind of monodromy around this moduli space of kind of symplectic structures. But it seems like you're not doing that. It seems like you're doing the kind of is there you mentioned a paper of yours maybe that actually worked this out?
Yeah, this B-side things, there are many papers. For example, if you know about the Bridger stability condition is a kind of expected to be a kind of universal covering of Kähler modular space, and people usually take the quotient of Bridger space by the autoequivalence of derived category. Then you will get a monodromy, right? And of course, Bridger modular space.
Maybe you mean, okay, maybe this is not really, maybe you don't really mean DB Koch, but some kind of, what do they call it? Heart of this abelian category or something changes the structure.
No, DB Koch itself fibers over string Kähler modular space.
Okay. Well, I will see if I can find something.
So yeah, I have said, so it is also expected that this local system is a categorification of quantum differential equation. And quantum differential equation is having some singularities, and also it has a natural D-module enhancement. So yeah, also it's usually regular and sometimes irregular, but so it's natural to expect. So since the decategorification can be extended to a D-module, it's natural to expect this local system can be extended to power schober.
Could I ask something about this picture as well?
Yeah.
So, I mean, you mentioned it would be generally irregular, and I guess you are the only person who proposed the notion of an irregular perverse schober, as far as I know. And there, in that paper, in the categorification of Legendre knots, there's a sort of extremely mysterious, extremely interesting statement, which I think it's something like nearby cycles of. So it's like this derived category, this DB-co is kind of nearby cycles of irregular perverse schober.
Yeah.
So that can you explicate that statement at all, or is it too much of a just a slogan? Because I mean,
yeah, it's just a slogan, but yeah, nearby cycle is just generic stock or something. So maybe let me come back later. Yeah.
Okay.
Okay, so it's natural to expect such thing. And so, but yeah, an obvious obstruction is that there is no notion of a complex of categories. Yeah, so since power sheaf is a complex of sheaves, at least one should have, to get a categorification of power sheaf, at least one should have the notion of a complex of categories.
Can I ask something about that as well?
Okay, yeah.
Sorry, because I mean, this has been said about it has been said a lot. There's no notion of a complex of categories of stable infinity categories, but there certainly is such a notion due to the very people who are saying this, so Dikharov, and so there is definitely a very good notion of a complex of stable infinity categories. So, but nobody seems to be making an effort to formulate this perverse schober definition in terms of them. I don't think the formalism of complex of categories is the problem. Certainly it does exist and is used in different contexts, somewhat exotic.
Oh, really?
Yeah.
But then you should try.
Well, I hope.
Yeah. I don't know, but yeah, actually I haven't thought about it seriously, but yeah, but yeah, somehow it's very, how to say,
So the Dikharov himself formulates a Dolt-Kahn correspondence for stable infinity categories, and there clearly a notion of complex of stable infinity categories can be formulated in terms of that. I mean, certainly in that paper, and it's been used more recently in other contexts.
So is it a correct notion in the sense that if you take the decategorification of that complex of categories, you will get a complex of.
I'm not sure about that, but I think that Dolt-Kahn correspondence does decategorify to the usual one. I mean, to some version of that. So I mean, I'm asking this only because I'm not sure the problem is with the complex of categories framework, but the sort of.
I mean, so you can of course consider the notion of complex of categories in various ways, but people don't know it is correct or not. I don't know. So.
Right. I don't know how one discusses support condition or something like that. So in that context, maybe. Yeah.
Maybe you should try. Yeah. Okay.
Sorry. So then, why are we doing this? You said that the first times kind of Kapran was giving talks about it. I think he was really saying that he was kind of selling this structure as something that's associated to a Landau-Ginzburg model. But now you're saying that's not interesting. So what are we trying to do? What is the goal? What is the thing that we don't have a good answer to what question? What is the thing that we're trying to define? What do we want to accomplish with this definition?
I mean, so if this kind of things, by taking
categorify, there's no, for example, do we expect that the Riemann-Hilbert correspondence will categorify as well?
That's a good question. But yeah, also it's difficult, I think. Yeah. So you mean is there kind of the notion of the schober or something like that? Yeah, I have tried it, but yeah, I'm not succeeded. So.
So I mean, I think I have more like an existential question. Like, why I really thought that the reason why we were trying to do this perverse sheaves was that this was the kind of right structure to put on a lambda, the base of a lambda Ginsburg model. Like that's how the talks were given in the beginning.
Answer. It's one answer. Or also,
what's another answer? Like, can you give a second answer?
For example, the power schober is a right structure existing on the whole string Kähler moduli space.
Okay, I didn't understand that either. So.
Also, I don't know much, but there are some representation theoretic contexts, I think. Yeah.
Oh, there's the stuff on the sort of hypergeometrics, so perverse schobers in the context of hypergeometric equations.
Oh, really?
That sort of certain categorifications seem to give rise to perverse schobers pretty straightforwardly. So it seems to be, I mean, whatever your definition of perverse schober is, I'm thinking of the only definition that exists is the quiver one, I guess. Right? The real definition is that. So that structure seems to be in a few places. So it seems to be a like genuinely interesting thing.
I see.
Also things like, I guess, the original sort of Seidel. I mean, you get like, will you talk about like semi-orthogonal decompositions or things like that, or is that too specific? Anyway, I'll make that a question later.
Well, one maybe reason why Kapranov is interested in trying to categorify perverse sheaves is that using Grothendieck dictionary of sheaves functions dictionary, he wants to categorify maybe actually the automorphic representations appearing in Langland's program, maybe to develop higher dimensional Langland's program. That's my that's how I think.
Possibly, I don't know.
So you're saying he's trying to get to a simpler object by categorifying. He's trying to find kind of a reason behind the existence of certain things. Is that something?
Is it a question to me or?
It was a question to him. It was saying.
Okay.
But
well, I mean, you see, when one starts generalizing things, sometimes things become much simpler.
Okay, let me continue. Okay. But is this 1 hour talk or something? 1 hour 30 minutes? What time?
Yeah, let me check. So it is 3:30. Let's say you have 10 more minutes, let's say.
Okay, 5 more minutes. Okay. I haven't defined.
Well, or maybe in future you can deliver a sequel of this in future, a continuation of your seminar talk in future.
maybe let me finish in 5 minutes. So yeah, Kapranov-Shishman's approach is somehow very combinatorial. Yeah, maybe many people here know, but so there is a classical result of due to the demodular people or power shift people that the power shift of this kind. So as I said, so D is unit disk and 0 is only singularity of this power shift. And the category of such power shifts is equivalent to the category of vector spaces with these morphisms. So VW just finite dimensional vector spaces. And UV are linear morphisms, and the condition is ID minus UV is invertible. Then this implies ID minus VU is also invertible. And the functor is given by taking the same local homology. So the point is, so power shift has certain property called pivot that, yeah, for example, in this situation, if you have this kind of local cohomology, they become vector spaces, not complex. And for example, so for constant shift, the corresponding data is this kind of zero and k, and with zero morphisms. And for skyscraper shift, you will have this kind of data, and so on and so on. So yeah, power shift is somehow very exotic abelian category, but this category is somehow very directly an abelian category. So it's very, so there are no complexes on the right-hand side. So it's very straightforward to categorify, and not very straightforward, but it's possible to categorify this right-hand side. That is the idea of Kabaranov-Shechtman. And so, yeah. So power schober on this space is modeled by this kind of description. So we have two enhanced triangle categories and exact functors between them. Then there's one exact functor and also adjoints. And if you consider, yeah, this kind of cone of adjoint morphism, then the condition says that T is an equivalent. And plus we have to assume some compatibility conditions between these left and right adjoint. And by taking K0, you will have K0 tensor some base field K, you will have two vector spaces, and this T becomes ID minus composition of U and U star, then you will get this data, and which is a power shift. So this is a categorization of the notion of power shift. And this definition is known before before Kabaranov-Shechtman as spherical functor. So here I will not give an explanation of spherical functor, but it has a certain history. So it's started from the theory of the Riemann surfaces. In the theory of Riemann surface, you have a functor, you have a different morphism called dense width, which is a topological generator of the mapping class group, and it has a lift to the notion has a lift to Fukai category by Seidel. So if you have a symplectic manifold and Lagrangian sphere, you have a dense width functor on the Fukai category. And motivated by homological mirror symmetry, conservation and Seidel Thomas gave a definition of spherical twist along spherical objects of triangle category, and the notion is further generalized by spherical functor. And so it's a very complicated history, but it's kind of certain generalization of twist equivalence along certain object. So there are various examples. Maybe I cannot talk about very much, but yeah. Yeah, this is just a spherical twist along spherical object. And also there is very interesting theorem by Ed Schiller, which says that every autoequivalence is a spherical twist. So every autoequivalence can be realized as T over spherical functor. So every autoequivalence can be upgraded into a power schober. So it is very parallel to the theory of power shifts. So any local system can be upgraded to a power shift. But the upgrade, so that upgrading is not unique. And so a power schober on Riemann surface is consists of several spherical functors around the singularity. So if you have Riemann surface and singularities, then you have to consider spherical functors. And you also assume that, so associated to spherical functor, you will have a monodromy autoequivalence here. So you have to assume the compatibility of such autoequivalences, which is a demand from the fundamental group. Maybe I should wrap up. So, of course, this this choice of description is very artificial, and there are several options. For example, you can take this kind of intervals, and you can consider the local cohomology along these points and these points. So, in the previous description, I took local cohomology along this, but you can also take this kind of spine and local cohomology. Then you will again get a very abelian description of power shift, and you will get a notion of a spherical pair by categorizing this notion. So this is also a possible categorification of the notion of power schober. So of course, there are more options. You can increase number of these intervals and taking, you can take local cohomology. So to overcome this very annoying situation, Diekerhoff, Kavarov, Shechtman, Soeberman's program, very ongoing program, will give a very unified description of such abelian description of power shifts. So I think this paper is already on arXiv. So which says that you can describe the category of power shifts as a kind of sheaf, not complexes, but using very exotic grothendieck site. Exotic grothendieck site. So whose open subset is so-called Milnor subset, and maybe you can refer to that paper. And so they defined the notion of Milnor sheaves. It is actually a sheaf, and they proved that the category of power sheaves is equivalent to Milnor sheaves. So using this description, they will eventually construct the category of power sheavers using this description Milnor sheaves. So this is, I think, a good, how to say, at least for Riemann surfaces, this is, how to say, correct definition of power schober. Okay, let me stop here. Thank you.
Thank you very much, Tatsuki. It was a wonderful and really very informative talk. I really enjoyed it very much, and I'm sure all of the listeners enjoyed very much. Uh, I think we have discussed all the questions while you are giving the seminar. So, but let me ask last time, are there any comments or questions?
Also maybe someone asked about irregular perturber, but yeah.
Right. But I mean, that can be, that might be a little bit of a tangent, but
Okay.
I was actually wondering, this is a more sort of more marginal question, I think, but this discussion in terms of Milner sheaves, I wonder, because I've seen some people reformulate. I mean, this is an idea that's not been tested, I don't think, but I've heard people discuss it. Is sort of using things like exit path categories and formulas of that sort to really wrap up, you know, that at least the formal construction of perverse schobers. Have you encountered something like this? Has this been done anywhere? Or I mean,
so you mean there is the possibility to define power schober in terms of exit path category? You mean?
Sure.
I don't think so. I'm not sure. So exit path category is somehow clear description of constructive sheaves, right?
Right.
So
right.
It's not power sheaves.
Right, but I think it is possible to. Well, maybe that's also that step also could not be categorified trivially, I guess. Right.
Yeah, but yeah, I think this expression is very close to exit path.
Right. I mean, that's why it seems very close to that. I mean, the Milner description is very outlandish. I don't. I'm not sure what's going on. So that's why, you know, I thought maybe. Right. But then irregular perverse schobers, I guess, are. I mean, this question is very interesting to me because I wanted to thank you separately at the end of this talk, but I guess I should do now because I gave a kind of little expository talk on your paper on irregular perverse sheaves.
Oh, really?
Summer school, and I had the opportunities to study it in great detail. And I mean, I had some trouble understanding some of the constructions, but I thought it was very interesting. So then I was going around asking people, has anybody done this type of thing for irregular, like perverse schobers? Does it kind of help us formulate such a thing? And then nobody really knew the answer. Then I realized you actually did kind of offer an answer in your next paper, which nobody actually knew about, actually. You know, but you didn't really use that notion in later.
I didn't. Yeah. So yeah, my project with Will Donovan is somehow now stopping. So, but I think maybe I also have mentioned in my paper that there is a work of Sanda Shamoto.
Yes. And Shamoto was actually in Istanbul like 2 years ago, and he gave a talk on that paper.
Yeah, it's essentially irregular schober, yes.
Yeah.
So it's very useful to formulate the generalized Dubrovin conjecture.
Right, but is there any work concretely in that direction, or is it kind of frozen right now?
You mean Shamoto's work?
Right.
I don't know, but
and your take on the Dubrovin conjecture as well. So is there work adding more
I'm
to
not
that?
studying. Sorry. Yeah. Yeah, I think there are several, let's say, things we have to do around the theory of irregular power schober. For example, as I mentioned, so yeah, in the mirror symmetry context, this kind of local system of power schober should be a categorification of quantum differential equation. And recent work of Iritani about the mirror symmetry, about the modular space of toric varieties. So that kind of quantum differential equation is having a certain irregular singularities, reflecting the semi-orthogonal decomposition of the derived category of coherent sheaves over toric varieties. So such derived category of coherent sheaves should be organized into irregular power schober, but yeah.
And then you think the notion you offered in that paper is adequate for that, or should one work on the foundations as well? Because it is a very economic paper, very.
Also,
It's full of suggestive ideas, but it's not expanded. So I'm wondering where to go.
Yeah, so I'm not expanding, unfortunately. Yeah. So recently I'm doing very different things. So I'm sorry. If you are interested, you should do. Yeah.
Any more questions or comments? So I will stop the recording now.